It's a great pleasure to have Fei Feng presenting today at our seminar. Fei is from UCLA, and she's doing a PhD in math, and she is in fourth year. And we are lucky to have her gravitating gradually towards reinforcement learning theory. She has written papers about optimization, reinforcement learning. I think she has a wide range of interests, yeah, it's a great pleasure to have her. So let's get started.
Thank you. Thank you for the introduction. So I first want to say that I opened two computers. So if the audience see me weirdly looking at the other direction, I'm actually looking at you guys. Yeah, and so I first want to thank Chaba, Gergely, and Kira, and also Alex for organizing this wonderful event and the current situation. I also want to thank previous speakers for their nice presentations, and I personally have learned a lot from their talks. So for today, I'm going to introduce one of our recent results, which is a novel reinforcement learning framework that utilizes unsupervised learning to help exploration in high-dimensional space. And so briefly speaking, the idea is inspired by some empirical successful readouts before. And this framework is designed to be general and simple enough to implement in practice, as well as provably efficient. I want to also thank my wonderful collaborators. So please allow me to introduce them. They are Ruosong Wang, who is a PhD student from CMU CS department, and Dr. Wotao Yin, who is actually my PhD advisor, and also now a member at Alibaba's Damo Academy. And also Dr. Simon Du, who has just finished his postdoc at IAS and is about to joining UWCS department as an assistant professor. And also Dr. Lin F, who is an assistant professor at UCLA's ECE department. Okay, let's get started. So let's first lay the foundation for this reinforcement learning by introducing this episodic Markov decision framework. So for this framework, we have S stands for a finite space, a finite state space, and A is an action space, and the P is a collection of transition kernels. And for different levels, we may have different transition kernel function. And R is a collection of reward functions at different levels. And H is the length of horizon. So for each episode, the agent starts from an initial state of the environment S1 and takes an action A1 to act back on the environment. The environment returns a reward signal R1 back to the agent and then transitions to a new state S2. And then the agent keeps select a new action A2 and go on. And this process keeps going for each steps until it terminates at certain state SH+1. And the rule that the agent follows to select actions is termed as a policy. And throughout this talk, we'll only discuss deterministic policies. And given a policy, we can define the value function, which is basically the expected cumulative rewards over these H steps following this policy pi. And the goal of reinforcement learning is to find a policy that can maximize this value function without the knowledge of transition kernels and reward functions. So to achieve this learning goal, we can see that it's very important for the agent to sufficiently explore the environment and try to identify all the opportunities for high rewards. For example, in this classical navigation problem, this agent's current location is, sorry, let me turn on the laser. So the agent current location is at this green dot, and it can go 4 directions, go up, go down, go left, go right, as long as it's not against the wall. And when it takes its actions, its location in this grid world is changing. And if it only stays in this gray blocks, then there would be no effective reward signals. And only when it can successfully reach this red point, it will receive a giant positive rewards. And we can see that because of such a reward function shaping, an optimal policy should be a policy that can sort of help this agent to find this red block as fast as possible from any point in this grid world. And to construct such a good policy, it's very important for the agent to realize the existence of such a red block. And this awareness is impossible if this agent does not explore the environment sufficiently enough. Okay. However, exploration is never a trivial task because we have two difficulties to overcome. On one hand, we need to balance between exploration and exploitation. For exploration, we always want to try new actions and hope these new actions can lead us to new states that will generate higher future rewards. However, this is not always true because sometimes these actions may lead us to dangerous zones and give us a big punishment. And in terms of exploitation, it means that we play optimally with our current knowledge about this environment. And although exploitation may not promise long-term rewards, but it still have certain guaranteed short-term profit. Therefore, exploration versus exploitation is like whether you want to choose to take a risk or you want to play safely. And the second difficulty is, so in a lot of real applications, what the agent truly observes is not like this clear, simple global view about its location in the environment, just like this left figure. And what it truly observes is like these raw pixel images from its sensors. So we can see that compared with a left compressed representation of its current state, what it truly observes is, so first of all, these image signals are embedded in high-dimensional space. And then sometimes these image signals can only give you a local knowledge of where you are in this environment instead of this global view. Therefore, when facing these two difficulties, an important question is how can we still design smart exploration strategies while we have cumulative knowledge about this environment? And in terms of systematic exploration, we have intensive studies in literature that with a tabular implementation. And this paradigm shows a typical learning process of this tabular-based exploration. So how they do it is, for each episode, an exploration policy is proposed, and then we execute this policy in the environment, and then we can obtain a trajectory of state action rewards. And then we extract the information from this trajectory and cache them in the memory together with all previously learned trajectories. And based on such information, we can then generate a new exploration policy and start over. And for this method, because they normally need to maintain a giant table in the memory to cache this necessary information, that's why they're termed as tabular-based exploration. And if we check over this list, we can see that tabular-based exploration has oh, sorry. I saw someone asking my mic is off. So if we check over this list, we can see that tabular-based exploration has a fairly complete theoretical understanding. And in terms of sample complexity, it takes this many number of episodes to learn a near optimal policy. And we can see that's the sample complexity that on the good side, it's nearly minimax optimal. But on the bad side, it depends on the cardinality of the state space. Therefore, if we have too many states or if we're dealing with continuous state space, then these tabular-based exploration strategies are basically inapplicable. Okay, so let me summarize a little bit here that we have this exploration challenge in reinforcement learning. And what has been well understood in theory is something with a tabular implementation. But in reality, a lot of problems have rich observations. And if we directly treat each observation as a state, then this tabular-based exploration is not applicable. Therefore, how can we connect this well-studied area with realistic problem solving is what we really should consider now. So as I mentioned before, a lot of reinforcement learning problems in reality has a giant number of observations or even continuous space of observations. And then people found that it's actually not necessary to treat each observation as an individual state. So for example, if I just change my position a little bit in this environment, or if I just rotate my camera a little bit to another angle, then what I perceive about this environment is still basically the same as before. So because these observations are not informational independent, and so a more ideal solution is to congregate observations that share similar informations together as one hidden state. So for this graphical illustration, we can see that on the left part, we have each dot represents an observation. And instead of treating each point as an individual state in the Markov decision process, a better solution may be that we cluster them into 4 clusters. And then each cluster is a more compressed representation. And we treat each one as one hidden state, then we only have 4 states to study. So based on this intuition, a very reasonable structure assumption about the MDP is that what we observed are generated from a small number of latent states. So we have a lot of observations, but we assume there exists a small number of latent states that generates them. And based on this structure assumption, what we have while the agent interacting with the environment would be like this process, that the environment is currently at a certain state as, and the state is unobservable to the agent. And what the agent observes is a context generating from this state. And this context is, for example, some high-dimensional features. And then based on this observation to the context, the agent selected an action. And this action acted back on the environment and let it transition to another hidden state. And then another context is observed, another action is selected, and go on. So a typical example here is still in the navigation problem, that the latent state can be the location of this agent in this grid world, and it has a very compressed representation. And what the agent can observe is like this visual signal from its sensor. So I want to clarify here that I use navigation problems to illustrate this structure in my talk, but actually we can find more realistic examples that follows this structure. So it's not only restricted to the navigation problem. And so this structure is formally a POMDP, a partially observable MDP, and the number of latent states is much, much smaller than the number of contexts. So based on such a structure assumption, a very natural idea is that instead of learning over this context and actions, what if we just directly learn over these hidden states? And so learning over these hidden states can be explicitly or implicitly. Explicitly means that, for example, we can try to construct the mapping from every context back to its generating state. And then we can just do exploration on this hidden state. And implicitly means that, for example, we can identify certain low-rank structures of this problem setting, and then this low-rank structure may help us to reduce the sample complexity. Okay. So based on this structure assumption, there are some empirical successes in the work by Tang et al. In 2017 and Bill Mayer et al. In 2016. So how they do this is try to utilize this structure explicitly. And specifically, they use unsupervised learning to construct a state abstraction map. And after constructing that, each observation will, the observations will then be grouped to a small number of decoded states, and so that we can conduct previously learned tabular RL methods on this small number of decoded states. So this idea is simple and intuitive, and it also works pretty well in practice. But the question is, does it have any theoretical guarantee? Or if we want any theoretical guarantee from this rich observation RL, what should we do? Do we need additional assumptions on the dynamics? Or how can we extravagate this information while conducting reinforcement learning? In terms of theoretical readouts, we have this line of work. And so the first three works are based on function approximation. The high-level idea is that they're trying to find a function instead of a candidate set that can bestly represent the optimal value function. And during the process of learning, they identify certain low-rank structure such that the sample complexity only depends on this rank parameter. And it can be shown that in this latent state structure, that this rank parameter is upper bounded by the number of hidden state instead of the context number, so that they achieve polynomial sample complexity that is sufficiently small compared with we directly use tabular-based methods on the context space. However, we can see that for these first three methods, although they can achieve learning efficiency, they require either deterministic dynamics over these hidden states, or they are not computationally tractable. And so the question is, can we achieve learning efficiency while on the other hand also achieve computational efficiency so that we can truly use these algorithms in practice? And in the work by Du et al. In 2019, they choose an alternative route to solve this problem. So what they do is, first they assume that there exists a perfect decoder that can map this context back to this generating states. And then they're just trying to learn these decoders through certain clustering methods or whatever. And the things I want to mention here is that they also impose additional assumptions on the dynamics, which is termed as reachability, as well as identifiability. So the reachability means that every state, for every state, there exists a policy such that it can reach this state with certain lower bounded probability. And this condition ensures that every hidden state will be visited with certain probability. And the reason why they require this condition is because only when we reach that state, we can get context or the observation data from that state. And then we can learn how to decode back to that state. So in a word, if we want to directly learn a perfect decoding function over every state, we need to go to every state and collect observation data. That's why they need this assumption. So
there was a question in the chat, about unsupervised. So what do you exactly mean by unsupervised learning here? Do you mean that you only
good
care
question.
about observation space and there are no actions?
So here, when we say unsupervised learning, it mainly means that we don't need the reward function to guide us and adjust the learning parameters. For example, let's say supervised learning is what we normally see in value function approximation, where in value function approximation, the loss function is defined as a TD error. And to construct the TD error, we sort of need the reward informations. But for this unsupervised learning, we are free from what rewards we eventually get. We only care about what observations we have, and these observations are just relates with the hidden state instead of the reward. Yeah.
Okay, and then they are also not related to the actions or whatnot, right?
No, for this, in this setting, we assume we only have a finite number of actions. So the unsupervised learning mainly focused on how to decode this context to states.
Right, regardless of actions anyways.
Yeah.
Okay, good.
Okay. So in terms of all these previous works, our goal is, so we also want to directly learn an abstraction map or the decoder, because we can see that the last work is more practicable than the previous works. But we want to improve it by not imposing any additional dynamics assumptions anymore. And also, we want to achieve both learning and computational efficiency. Okay. So to achieve this goal, it's actually not that trivial. And so let me explain the challenges here. So the challenges here is, first of all, there is no prior knowledge of the latent states. You don't know how many latent states there are at each level. You don't know whether they have certain internal structure. So there is nothing you can utilize to learn these latent states. The only thing you can do is just to collect samples from them and then try to recover. Okay. And in order to learn a good recovering function, then basically you need to collect enough number of observation samples from the states. And in order to collect these observation samples, you should first reach these states, right? But in reinforcement learning, it's not like you want to reach there and then you will reach there. So, so the things here is, in order to learn a good abstraction map, you need to collect enough observation data. You need to visit this state. You need to visit every state sufficiently enough, but it's not within your control because you don't know the dynamics there. So this interplay between, on the one hand, learning abstraction map, and on the other hand, achieve efficient exploration in reinforcement learning makes this whole thing challenging. Okay. So our solution is following the same principle as the empirical work, that we use unsupervised learning to learn certain decoding functions, such that the high-dimensional observation space can be reduced to a low-dimensional decoded state space, and then we can conduct tabular-based RL to guide exploration over this low-dimensional state space. Okay, and so in conclusion, our high-level idea is to simulate the process of running tabular RL on these hidden states. Okay, so on one hand, we need to guarantee that this supervised learning oracle can return us a sufficiently good decoding function after seeing enough many of samples. And then on the other hand, we need to guarantee this tabular RL algorithm is provably efficient in terms of exploration. And these two things are actually guaranteed by a lot of existing works on the area of unsupervised learning and on the area of tabular RL. Okay, so we can see for this learning structure, at first we don't need any additional dynamics assumption. The system can be arbitrarily stochastic as if it wants. And secondly, our framework is pack learnable, and our sample complexity only depends on the number of hidden states instead of the number of contexts. So we achieve significant dimension reduction as previous literature work compared with traditional tabular-based RL, if we want to apply them on the observation space. And certainly, the choice that we can use for this unsupervised learning oracle and the choice we can use for this tabular-based RL is quite general. I will give a more concrete requirement on this, but basically, in practice, we conduct a preliminary numerical results, and we found that this is basically arbitrary. And it would be even better if you have certain prior knowledge of this observation structure, then you can directly select a suitable unsupervised learning oracle for your problem. And lastly, our algorithm is super easy to implement because we only take two components, and both of them are very easy to implement. And you can just use some current existing Python packages, for example, and there are plenty of unsupervised learning methods that you can select. And in terms of tabular-based RL, they're basically just a few lines of code. Okay, so till now, let me summarize again. So till now, we proposed a framework that satisfy what we want in the beginning. So what we want is we want to find a provably efficient exploration strategy in the reinforcement learning problem with rich observations. And no additional dynamics assumption is proposed, except for that there exists a small number of hidden states. And we achieve both learning side and computational side efficiency. And this framework is general and flexible enough so that you can utilize almost whatever things you want. So it's like a plug-in method. And now let's take a deeper look at why and how we achieve this provable efficiency. So we said that our high-level idea is to simulate the process as directly running tabular RL on these hidden states, right? And recall that the learning process of the tabular RL is that for each episode, we propose a policy over the states, and then we generate a trajectory while executing this policy in the environment, and then we get a trajectory of states following this pi. And then we feed this trajectory to this algorithm, and then we update our exploration policy. So this is a framework that if we can directly see the true latent states. However, now we don't know this. We don't know these states. They're hidden. They are hidden from us. So we only have observations to the context. That's why we need to utilize a decoder. So on one hand, since this proposed policy is from hidden states to states to actions, so we first need a decoder that can map this context to state first. And then we use this policy pi to select actions. And on the other hand, what we generate is a trajectory of context. So we also need this decoder to help us translate back to a trajectory of states. And more importantly, we hope that after this translation, we truly can get a trajectory as if we're running pi directly over these hidden states. Okay. But of course, the decoder function is initially inaccurate. And so how we correct it is, so given certain decoding function, we put it together with this policy pi, and then we make a composite policy over context action space. And then we just execute it in the context space for many, many times, and then we can generate a lot of trajectory of this context. And then we use unsupervised learning over this observation data to refine our decoder function. So after each rollout and refinement process, we will have a more accurate decoder. And most importantly, as I mentioned before, the key challenge is if we want to find a decoder that is actually on every state, then we need to guarantee every state will be visited for enough many times, right? But in this learning framework, we actually don't need that. What we truly need here is this decoder function should be accurate on states that is frequently visited following this policy pi. For example, if there are 20 states, but only 5 states that will be frequently visited following pi, then we only need to be very correctly decoding these frequently visited states. Okay, and a more explicit explanation is like this. So, for example, right now we have the true decoding function. Then combine this true decoding function with this pi, and we run it over this context space. Then it's just as if we're running pi over hidden states, right? Because this true decoding function can first decode every context to this true latent state, and then we select actions. Okay, and now since we don't know what this true decoding function is, and after learning a lot, we learn another decoding function, which might be inconsistent with the true decoding function on a lot of states. But as long as this decoding function is consistent with the true decoding function on the states that pi will frequently visit, then in probability that what we will so we always can truly decode the states that we will frequently visit. So on this frequently visited state distributions, we're doing exactly the same as if we know the true decoding function. Okay, so this is like the intuition, and this is also the reason how we overcome the key challenge here, the key challenge as I mentioned before. And the reason why we can refine this decoder step by step is because of the property of unsupervised learning, that as more data we collect, a more accurate decoding function we can generate. So yeah, just as I said before, this decoding function's accuracy gradually grows, and finally we can reach something here. So for the audience to have a better understanding within this short amount of time, I draw this graphical examples for you. So here we have this many states, and they are hidden from us. And given a policy pi over the states, this green colored dots means the states that I will frequently visit. Okay. And so we start from an arbitrary decoding function f0. And pi circ f0 is generates another policy. And because this policy is different from pi, therefore it visits different states with high frequency. But it's okay, because even though this distribution is different from this distribution, we still collect enough many data, right? And so after a round of refinement with unsupervised learning, at least now this newly output decoding function can successfully distinguish these 6 states. Okay, and then we can see the first 2 layers is the same as these first 2 layers, which means that we can distinguish what is S1. We can distinguish between S2 and S3, and because of this successfully distinguishment, that we will do exactly as what the pi will do, because we successfully decode them correctly. And following pi at the 3rd level, from these 2 states, we will reach this state with high probability. Therefore, from these two states, we will reach these states with high probability. But because we've never seen these states before, right? So we cannot distinguish this state from this state at the same level. However, we're still able to collect a lot of, we'll still be able to collect a lot of observation data of this state. So after another time of unsupervised refinement, we are able to distinguish this from this. And a special cases for this is 5 because we've never seen it before. So very possibly we will just put the context from this one to either this one or either this one. But it's okay because pi only visits this state with very small probability. So even if we make mistakes on these observations, it won't affect us on large scale. And so eventually, this decoding accuracy propagates level by level, and then eventually we can cover every state that is frequently visited by this pi. And we can see, compared with the previous theoretical readout, which wants a decoding function that can accurately distinguish every state, we only need to successfully distinguish the states that will be frequently by this policy.
So
that's why we
clarification question. What's the meaning of the blue notes? We were guessing what the meaning is, but
the blue nodes are the nodes that we can successfully decode, but they are not required by this policy pi.
Right. Okay.
Yeah.
That's what I thought. Yeah, and so you're explaining this for a fixed policy pi, and I guess that's going to be the logic underlying the proof that like you have a pi and then you're kind of like fixing up the decoding function for a while.
Yes, exactly.
Once it becomes good enough so that, okay.
Yeah.
Do you have a number of runs that you can run for any policy that after which the decoding function is guaranteed to give you a good decoding, or can you detect this based on the data, or do you have to have some additional knowledge about how fast this decoding correction happens?
Yes, very good question. So first of all, we cannot guarantee that after training many times, we can find a decoding function that will be accurate on every state.
Sure.
But we don't need that.
Yeah.
Because so for each episode, given a policy, we just run this until we can generate a trajectory that is good enough.
That is
and we can
resembling the trajectory that you would generate if you knew the perfect decoding function.
Yes.
Right. Yeah.
And the number of trajectories it needs is polynomial. And then because by tabular RL, we will only have this whole thing for polynomial number of times. So the product of these two things is still a polynomial. Yeah, I will illustrate the detail of this algorithm later, and then you will have a better understanding.
Okay.
So can I also a quick question here? So this slide convinces me sort of that this procedure is going to be self-coherent in a way that it's going to terminate in a reasonable way, but it doesn't guarantee that it's going to be correct in the sense that it returns the right kind of decoding on the states. This is just coherent, and that's enough.
This is exactly what we do, and this is also a demo of how we prove actually. So I will show a more detailed proof sketch later, but basically we just follow this process. But of course, in our proof, we do not assume that these decoding functions are level by level correct. In our proof, we only need to show that for each iteration, there is at least one more state that will be truly decoded. And because there are only finitely many states to cover, so after a fixed amount of time, we can eventually cover all the states that is frequently visited by time.
Yeah. Right. Yeah. Okay. That makes it more clear. Thank you.
Gerge, I would turn the question back to you, like, how would you even define what's the correct decoding function? You would require that there is a permutation of the decoded values that gives you exactly the correct states? That's the definition?
Well, I guess by correct, I would mean
yeah.
that there is a smaller set of states, and then you exactly recover those states, and you don't introduce any others, and you don't
we will
lump
have
two
a
states
more
together.
mathematical.
Right, yeah. So let just Fei finish. Yeah, I guess she knows what
Yeah,
what
we'll
she's
have a
getting at.
more.
Yeah.
Yes, in terms of the question that about the correctness of the decoding function, we'll have a more detailed description later, and we will also have a mathematical formulation about how this supervised learning oracle works.
Very good. Thank you.
So that's why we can get the quantitative readouts. Okay. So this is just a short view of the numerical test that we run on this combination lock environment, which is designed to be difficult for random exploration. You can see that, so here the true latent states are only 3 for each layer, and the observations is proportional to the length of the horizon. So in this figure, we have h equals to 20. So what the observations are 23-dimensional vectors. And these red dashed lines are, we directly let one tabular-based exploration to see the latent states. And we can see that our method, which only sees observation, is very close to this skylight performance, which somehow testified, at least preliminarily testified, although even on this simple case, that our method is of high efficiency. And this shaded area characterizes the standard deviation. And I can tell you that with probability at least 80%, we can directly recover this red dashed line. But of course, our performance depends on how good the decoding function that we can learn. Because if we can learn this decoding function perfectly, then we're just doing exactly the tabular case. And for other methods, if we just feed this tabular exploration with observations, then you can see there is basically no performance, at least initially. Okay, so now let's take the last few minutes to go over the technical details. We have structure assumptions, an oracle assumption, and then the main readout. For the structure assumption, we adopted a previous work which proposed something called block MDP. So in terms of what we have before, the existence of this small number of hidden states, most importantly, that we assume the existence of a decoding function such that it can map every context back to its generating state. So you can see this assumption actually implies that different states generates different contexts, right? So that every context will directly map to one state. But actually, we can relax this a little bit, I guess, because when I go over our proof, I think even if two different states have a small number of contexts, and this context does not happen very frequently, I think we can still do it. So you can imagine that two dots in the space, and they have the observations are like Gaussian noise data, and this Gaussian circle have certain area of overlap. But if this area is small enough, or if this area doesn't occur, that with high probability, I think we can still do it. Yeah. So still, this decoding function is unknown to us initially. And more importantly, we have this mathematical formulation of this unsupervised learning oracle. So given an observation data, where if this observation data is generated following this probability, so this probability means that we first reach this state with certain probability, And then this Q is the probability that this context follows that's generating from the state. So it's basically it's a mixture model as in statistical learning. And then the unsupervised learning oracle can learn a decoder function such that with high probability, it is consistent with the true decoding function. So here are several things that I want to clarify. The first thing is that we can see the correctness is measured by this function. And this function will be smaller if we have more observation data. So as n increases, this one will decrease. This thing also complies with what we have for the unsupervised learning. That if we have more data to feed into this unsupervised learning oracle, then more accurate this decoding thing would be. And another thing I want to mention is that the correctness is described over this distribution. Therefore, this implies that the FX correctness is in general, but it can be very wrong over some particular state. So this is very intuitive, right? If for a state mu s equals to 0, which means we never get a chance to visit there, then of course we will be pretty wrong on it. And if mu s is large, then we have a large probability to visit there. Then because the total sum is small, the total sum of the error is small. That's why for that frequently visited state will be very accurate. So this is very intuitive and also complies with the classical unsupervised learning methods.
Okay, Fei, just to clarify, the notation is a bit confusing. So the first line says that xi is sampled from u of s and q, but I guess like what you have under the symbols PR in the grade box, that's the precise thing of how the data is generated. So the data is generated by generating some SI from u, and then given an SI from u, the XI is generated from the kernel Q, right? Given SI. Is that how the data is generated? Like what is S there? What is S there in that part?
Oh, S is the state.
Like, is it a fixed state? Just one state? Which state?
It will be just a one state because this context will, so each context only corresponds to one state.
For each I, you have a single state? It's a different state. SI, right? Like it's indexed by I too.
Yes. Sorry.
Okay. All right. Okay. Yeah. I think that we got it. Yeah. It's just the mixture model. Yeah.
Yes. Okay. The mixture model.
Yeah.
And also, I want to thank Chapa for this clarification. And this abstraction, this mathematical abstraction, also complies with what is used in this empirical work. And although in this work they use autodecoder, that's I believe that right now they do not have a complete theoretical understanding, but as long as there is a theoretical result, I think we can just simply plug in this SEM analysis with maybe only minor revision. And the example of this unsupervised learning oracle includes mixture model like Gaussian mixture model, Dirichlet mixture model, or something else, and also some clustering-based methods. Okay. So this is a more detailed description of this framework. So K is the index for episode. And at episode K, this tabular-based algorithm will propose the policy pi K. So right now, let's first ignore this dashed blocked part. Then given this policy, we put it into this routine, and this routine will return a trajectory. And this trajectory would be as if we directly run this over the hidden state, and then we put it back to this tabular algorithm, and then we just go over this loop. And now let's take a closer look at what is happening inside of this routine. So this routine is a for loop. And I can first tell you that this capital J polynomially depends on the number of states, the number of hidden states. And for each iteration, what we do is we define this. This is actually a policy, because F is certain decoding function that maps the context to the states, and then we can select action from pi_k. So the composite function is a policy over context action space. And then we use we just follow this thing. We can collect a lot of trajectories. And the second important part is we combine these newly collected trajectories with previous training data set. And then we feed this combined data set into the unsupervised learning oracle to learn a new decoding function. So we can see that this combination is very necessary because it guarantees that what previously decoding function can correctly learn, the later learned decoding function can also correctly learn, because we are learning over the data generated by the previous decoding function, basically. And then we need another step of match labels, because unsupervised learning might return as different labels at different times. And we have to keep this labeling system consistent so that the tabular-based method will not be confused. That's why we maintain this data set, which is served as a standard data set. And we swap this labels of this F tilde so that it is consistent with previous ones. And then we just keep going like this. And after polynomial number of iterations, this final output thing, we run this final output on the context action space, and then we can generate a trajectory of context, and then we use this final output decoding function to translate it into a trajectory of states. Then this trajectory of states is as if we're directly running pi_k over hidden states.
So I do have a question. Maybe it's too early to ask this question, but are you going to have a regret bound, or you have a sample complexity result? And then do you think that there is going to be a difference between like how you would analyze regret here versus how you would analyze sample complexity? You know what I mean?
Yes. I'm not very sure right now, because at first our result is we currently only have an implicitly polynomial readout. Yeah. So this one we don't know exactly what it is. But I guess we can obtain the same polynomial thing for regret.
So you can reduce, but it seems when you are running this inner loop, then your regret may be a little bit uncontrolled, right? So this inner loop is not going to run forever. So that's a good thing, but like it can go to wide places. Like there is no control about like where it goes, right?
I see
the decoding function is really bad, and there is no like monotonic improvement of decoding function between iterations. That it will be hard to control regret in a very gradual, like some way, like some crude way. Yes, you can control, but maybe you get a t to the 2/3 regret or something like that.
Yes. I think I agree what you said.
Okay.
And yeah, probably yes. When we train this decoding function, we cannot guarantee the performance. We cannot control these rewards. Maybe.
Interesting, but it's curious.
Yeah, but we'll I think we'll try to investigate more about this sample complexity from the regret side. Yeah, thank you for the question.
Yeah.
So maybe most people are interested in how we truly prove this mathematically. So still, we just need to prove that for each episode, we can simulate a trajectory as if we are running this policy over hidden states. And to prove that, let's first start with some decoding function. And then if this Fi can directly decode frequently visited states of this policy, then we're done. Okay, because then it's just like running pi circ with the true decoding function. Otherwise, if this second step is not true, then at least it collects more observation data. And then this newly learned function will then be correct on more states than fi. Okay, so let me illustrate more here. If fi is not directly, if fi cannot correctly decode frequently visited states by this policy, which means that following this policy, we can reach some state with high probability, but this decoding function is wrong on that state, right? And then, because we collect a lot of training trajectory following this policy, so we'll be able to collect a bunch of observation samples at that state that we cannot correctly decode before. And remember that these training samples following this will then be combined with this previous data set. And after unsupervised learning oracle, this newly output decoding function will then be very true on the states that this one will frequently visit.
Can I have a quick question here? So your assumption was maybe simplified a little bit, because the assumption about the unsupervised learning oracle stated that there is a fixed distribution mu, or like for any fixed distribution mu, the oracle is efficient, but here it's the distribution is shifting, and like maybe you're gonna apply corrections to that, or like you don't care, you're gonna like strengthen this, that like for every single I, maybe this mu distribution is different, and like, so how does this work?
Okay, so first of all, in this definition, this mu is like any distribution over states.
But fixed?
Yes,
single distribution.
Yes. We
So
fix one distribution, and then we collect a lot of data.
Right, but like if you go to the algorithm takes as input D. Like I'm confused about that. Like where is that D coming from? Is that the same distribution or not? And also when you are like learning and then changing things, you're merging the D with the D prime. And so every iteration is like a new distribution. If you're feeding all this data to the unsupervised learning oracle, like it's not confirming the assumption that you stated on the previous slide.
Yeah, I see your point. So first of all, I want to say that when we collect this D prime, we will collect a batch of them. Sure. So which means that for here, we would have, we fix this. So this policy induce a distribution over the states.
Sure.
Which is like mu. And then we have n of it as D prime. And so as you said that we combine a lot of data that following different distributions all together, right? So that this whole thing can be viewed as a uniform distribution over all these different distributions, right?
Okay. Right.
Yeah. And so on averagely, we will be true on all of these different distributions.
And you're saying that your assumption automatically covers the case where mu is the mixture of other distributions? I guess you're, because mu was arbitrary and like somehow
yeah.
So, but okay, maybe I believe that. It's possible.
I think for here, in terms of this mixture model, it's more important is about the distribution of this Q. So for example, in Gaussian mixture model, this Q follows the Gaussian distribution, and in other mixture model, it follows the different other distributions. So the generality of this sample oracle is not only about what distribution we have over states, but also about how we emit this context from these distributions, from the states. Okay. Sorry, I go over too much time. And eventually we have some open problems that we want to investigate in the future. For example, can we build explicit complexity redoubts, or can we relax the oracle requirement a bit? Yeah. Thank you very much. And I would like to take more questions. And I'm so sorry for prolong this talk for over 10 minutes. Yeah, thank you very much.
We had a lot of questions. Thanks. Yeah, in the meanwhile, the chat really fired up, and There's a lot going on between Lin and Nan, and like I think they should speak up. They should just
Yes,
have
yes,
a
yes.
discussion. So Nan, do you wanna summarize like how far did you get?
No, yeah, I was just asking Lin and the authors the question. So, you have this label matching step. I was wondering if instead you can do something more kind of brute force, that is like just to relabel all the data previously using my new decoder function and treat I have some tabular data, which is presumably like different from high label things before, but I can just feed this data to a PAC-RL algorithm and tell it that this is as if the data you have collected before, although they're different, right? So I think Lin's answer, which I think makes a lot of sense, is that at least their current analysis doesn't go through, right? Because their current analysis is assuming that this underlying tabular algorithm is only seeing a continuous stream of like coherent data. But I think in practice and also in theory, but I mean, of course, it would need much more, tweaks and new analysis. I don't see this as implausible, right? Because it's like saying that I have a tabular algorithm which explored for a while and accumulated some data, and I stop it and hand the data to a different PAC algorithm and let it continue, right? How can things go like too wrong? I mean, that's my guess, but and also like I was wondering like how does that work in practice compared to label matching? Because one thing I don't like about label matching, I mean, it really depends on how you do it, but I think this is related to a previous question, is perhaps some previous labeling is just wrong, although in theory you have this guarantee, but in practice or whatever, I always want to be able to use fresh, the latest decoding function, which uses the most of the data, and somehow being able to forget about the past, right?
Yes, you are exactly right. This is what I do in practice. So
okay,
in practice,
here we go.
Yes, in practice, we actually do not maintain this Z data, at least in my current implementation, because this converges very quick. And so what I do is exactly as you said, that I don't do this fixed label. I just restart with what I have learned if I'm very sure that this decoding function is very correct at that time. And then basically I just restart and then forget about what has learned before. Yeah, so at least in this numerical test, because this test is still simple and this dimension is not high enough. So what I have done and what you have suggested is still applicable here, but at least now I'm not so sure that whether this fixing label is also not necessary for more complex case. But yeah, thank you for this suggestion.
Yeah, follow up to Nan's question, I think we can actually have some variants to the algorithm. For instance, you can, let's say, suppose you have a policy that is guaranteed to visit a lot of states. Then you can just learn a decoder function based on this new policy, and then you rerun your underlying, let's say, tabular algorithm. I mean, of course, this one will, be worse than, let's say, polynomial factor in terms of S and in terms of sample complexity. But I think the analysis will still go through.
Oh, I see. I think like one hack is that you just discard all the previous data and like rerun the whole thing. Exactly. I think I was suggesting some middle point, right? Because you inherit the data from the previous rounds. Again, I agree. This will like totally mess up like the existing analysis of tabular algorithms, but
right.
Still seems plausible to me.
Yeah, of course. Yeah. So currently we're just doing like let's say black box reduction. So
exactly. Yeah, you can no longer treat the tabular algorithm as sort of like a black box. You need to open the box and really see the details.
Right. Thanks.
Yeah.
So I have some further questions, which are like a little similar to what Chava was asking about your oracle that you assume, regarding that, for all distributions, you need to be able to recover the decoder. So I guess here, since the data set is changing, and it's changing in sort of a nasty way that depends on the past observations, then I think that this mixture model is sort of going to be violated. So what I mean by that is that, for example, you have like two data sets lumped together after two iterations, right? The second data set is going to depend on the outcomes that you saw in the first round, right? Because your policy depends on it, right? And I'm just really wondering if your oracle can deal with this, right? That the data is going to be like dependent in a very nasty way. I mean, on a high level, I buy your response that you can treat everything as a uniform distribution over the past data distributions, but it's not that simple, or at least it doesn't look that simple to me because of this dependence issue.
Yeah, but
yeah, maybe I can
Professor Yang, can you answer this?
Yeah, I didn't see unmuted himself. So, yeah.
But basically, let's say in the algorithm, we actually run each policy for a bunch of runs, right? So although you get a new policy after certain runs, you get a new policy, you still run that for a bunch of runs.
Sure.
So then you mix out the data. So what's actually you get is a mixed distribution of all the previous policies.
Sure.
Yes, you have all the previous policies. You mix them together. You run this on the environment to collect a bunch of data. That the distribution is essentially the same.
Yeah, but my concern would be here is that if you reuse the past data, then the distribution of Q, right? So like the distribution of X given S is no longer Q, right? It is something else because of the dependence. Right?
Or
if
I can read
and everything, and then like the old observations are not really relevant anymore.
Yeah, sure. In terms of analysis, I guess you can. I mean, the most brute force way is just rerun all the policies independently.
Right.
All the data. But in practice, actually, especially for this unsupervised learning oracle, so what we really want is that you visit a state for a bunch of times. Actually, the distribution is not that important. The things that are important is really how many times you visit the internal state. So if you visit a lot of more times, then it becomes correct, right? Something like that. So because you can always match the distribution with the uniform distribution eventually. So as long as you visit a lot of times, then you can correctly decode the state.
Can I maybe rephrase Gergel's question or concern? I think the issue is that in this case, when you sample data in an adaptive way, the mu distribution itself become a random variable that depends on part of the previous data point X, right? I think that's technically a concern, although, I mean, I don't know how you guys do it with the current framework, but I agree that if you just completely like resample data from all previous policies, that should clean up the issue.
And then it's right, so you can do that.
Yeah, the other kind of thought on that is that in more standard PackRL, you always have this issue, right? That you generate data in a way that you choose actions based on previous data, and the way you deal with that here, they're usually like you do martingale or something like that, right?
Yeah, or you
that
do like a
massive
union bound or everything.
Yeah, Friedman or whatever. But is there any way to leverage any of that kind of argument so that you don't need to worry about these dependencies?
So Nancy, thanks. Yeah, so actually, we don't need to worry about that because in this definition of the oracle actually handles all the issues. So the oracle says that if you draw draw a sample from some distribution, then the oracle is correct. According to this distribution, right? So even
your oracle assumes ID data, right?
It assumes the ID.
The way it's written here, it is. Yeah, I guess you should extend maybe this assumption, and that would be an easy solution, because like you can imagine that if you have a good oracle, then it will be able to deal with the sequential data as well for the reasons you mentioned, Lin.
Yeah.
But it's technically, it's like this assumption seems a bit too narrow. But
yeah.
Yeah, so
So,
you cannot just use like union bounds over everything, because then I guess you're gonna pick up a factor of X, which you don't want.
So actually, what we do is like you first generate the distribution, the data, right? So you generate a bunch of empirical data, then you uniformly random sample from this data set. You can view these two processes relatively the same. So in our proof, that's that's actually what we do, right? So we
basically condition on the as part of the data.
Yeah, so yeah, you generate the distribution over the data, right? So then you get another distribution. Of course, you're generating a bunch of IID samples from this empirical data set. And then you can show that this two distribution is not too different because you really visit a lot of the internal state a lot of times.
All right. Well, I'm pretty sure that your analysis is very carefully crafted. So I guess I'm gonna take a closer look at the paper then. So
yes, thank you, Professor Yang, for helping me answer the questions.
Right. So let me just look for some more questions. So Sharon Maswani had a question. I don't know if that was already answered or no. Maybe you can ask a question or say if you're satisfied.
Yeah, it's mostly answered. It was the same thing, that if you keep reusing the same data, you might diverge out, and yeah. But rerunning, I agree, solves it. Yeah.
All right.
Arushi Jain had a question. Arushi?
Hi. So I have a question. For what I understand now is the way you're constructing your hidden states is in unsupervised fashion, right? So what if one starts taking into consideration your transition function and reward function, and then construct like abstraction based on that, something like similar to bias simulation? Like, would that help improve sample efficiency or not? Like, I just wanted to like see if there is some relation or not with respect to this work.
I guess maybe this is a question of how do you exactly place this work in the literature? You have, these other works that take into account transition structure as well, and it seems that you are very heavily relying on that every single observation can be decoded into a state, regardless of like what was happening before or what's happening afterwards.
Yes, so I think for this question, it's more like what do you want to choose? So if you don't want to rely too much on the structure, and if you don't want to rely too much on the oracle, then of course you need to impose a stronger assumption on the underlying dynamics or the shape of your reward function. But because we already have some previous works that is doing this, and so what we are doing here is we focus on the generality of this framework. That's why we do not impose more dynamic assumptions. But of course, I think this is an interesting direction to look at in the future, that whether we can impose some minor dynamic assumptions such that this decoding function can be relaxed, and this oracle can also be relaxed. So this is also what I wrote in this future work. Yeah, thank you very much for your question.
Thank you.
So Kamyar had a question. If you're still here, can you ask it? If you're still curious.
Hey, yeah. So I think Nan partially. Hey, thanks for the talk. Nan partially answered that. What the question was? What's the difference between ROM-DP, which is a rich observable MDP, and block MDP, like in more detail?
So you say that Nan has already asked your question, or do you want to think from me? So because
I guess he's just asking the relationship between this setup that you have, this block MDP assumption, and this rich observation MDPs. Can you say anything about that? Whether these are the same or these are different somehow?
I think they are different, or maybe I think. And also when I go over the literature, I found that this block MDP is more like a special case of this rich observation RL. If I recall correctly, that in this previous work, for example, in these previous 3 works, they actually build these readouts without assuming this block structure or this disjoint context structure. So I would say that this disjoint observation structure is more like a special case of this rich observation. And this rich observation setting can...
No, Kamir is talking about something different. So the rich observation MDP he talks about is more specialized and very similar to block MDPs. Maybe Kamir can provide a link to. I think on a first order approximation they're the same. So he actually has a link in the chat.
I think Akshay's paper also is on, it's on the function spaces, but it's still ROMDP is subset of that setting, right? I think Akshay's paper is also a good link.
So can you guys just recite the definition of rich observation MDPs?
Rich observation MDP is you have a surjective mapping from latent state to observation. Basically, there's a deterministic mapping from observation or context to the latent state.
Okay.
But from latent state to observation is a stochastic mapping, but from observation or context to the latent state is
there is a unique decoding function.
Yeah, so I don't know. It's like a block MDP is probably similar.
It seems.
I think by your definition, it might be the same.
Yeah.
I
think it's just terminology.
Yeah.
Yes.
And actually, I could cite some literature, I think, from 70s when people gave it. Because, I mean, like, it's an obvious thing to think about. It's a nice structure. Very nice. Yeah.
Yes, thank you for sharing the links. I'll go over it afterwards.
So in your future work, you mentioned that that you want to improve over like the explicit dependence on all these parameters like states, actions, and so on. I guess that's what you mean by more explicit complexity results. So can you say something about the current scalings? Like what is this polynomial that you mentioned there on the previous slide?
I think the main reason that right now why we don't have this is because for this oracle, we don't know exactly what is happening inside of this G function. So if we want to establish more explicit sample complexity, then we have to analyze this case by case. And then I think utilizing existing theoretical readouts where this G can be explicitly expressed, then this whole things can be all combined together. Because in our algorithm, that's how many episodes it takes and how many iterations it takes is kind of already sort of explicitly represented already. And the only thing that is hidden inside of this black box is this G function. Yeah.
All right, but can you give me like a quick intuition about how the final bound depends on this G n of delta? So if it's say like, square root of log 1 over delta over n, then what would your bound finally become?
I think I kind of forget the explicit form of what is happening on the rest part. But in our final readouts, we assume that if we want to achieve certain accuracy here, and we take the inverse function of this G to figure out how many samples we need, and we assume this inverse function will depend polynomially on the accuracy parameter as well as this delta, and then we establish this polynomial sample complexity. And in terms of that, how many S and A and H here, sorry, I really kind of forgot here. And I also think that there are plenty of rooms to improve it. Yeah, if we have a more explicit, or if we can design this workflow in a smarter way. But if you're really interested, you can still go over to the paper for the induction.
I guess what I was like sort of curious about is just in a high level, like what is this polynomial in terms of S? Is it like S to the 16 or S to the 200 or something reasonable like S squared or maybe linear in S?
Oh, yeah, actually, even if you go over our paper, I think you won't have an explicit idea of that. It's still, because every induction, when we prove it, we need to rely on the on that G function, and so everything is hidden from the first step always to the end.
I see. Okay. Yeah. Thank you.